Welcome to the deep dive. In today's world, we're just swimming in information, aren't we? We're here to maybe throw you a lifeline, cut through some of that noise, and get to the really interesting stuff. Today, we're embarking on a pretty fascinating journey, I think, right into the heart of enterprise storage and infrastructure. And our source material for this deep dive is, well, it's a bit unusual. We've got a collection of technical exam practice questions. They're focused specifically on HPE storage solutions. Now, before you maybe tune out at the word exam, trust us, these aren't just dry questions. They're actually these brilliantly concise windows into real-world challenges. The stuff that keeps our digital world humming and the ingenious solutions designed for them.
Exactly. What's really fascinating, I find, is that by looking at these very specific scenarios, these technologies, we can kind of pull back the curtain on really critical aspects, things like data protection, high-performance computing, resilient infrastructure. It's not just about passing a test, right? It's about understanding why these solutions matter. Why are they built this way?
Right. The why is key. So our mission today is really to extract the most important nuggets from these technical deep dives. We're looking for those aha moments, the things that show you not just what a technology does, but why it's maybe indispensable and what real-world problems it's actually solving. So let's unpack this and dive right in.
Fortifying your digital assets, ransomware, migrations, and disaster recovery.
Okay, so we're going to start with some of the most, I'd say, pressing concerns for pretty much any organization today. How do you protect your data from, malicious threats, and how do you ensure business continuity? Let's kick off with ransomware. It's everywhere in the news. Imagine a customer, they're really worried about sophisticated attacks. They need backups that are absolutely fundamentally unalterable. Even if an admin gets compromised, maybe their credentials are stolen.
Yeah.
How do you actually achieve that level of bulletproof protection?
Yeah, that's a huge concern. And this is where something like HPE Virtual Lock on their Store Once appliances comes in. It's really powerful. It provides what's called Write Once, Read Many protection, WORM for short. When you enable it, it literally prevents deletion or modification of those backup sets for a defined period, of course, the retention period. This mutable design, it's just crucial for defending against ransomware. It ensures that your backup data stays intact, it's recoverable, even if malicious actors get in.
Wow, so immutable. That means truly untouched. That's a huge peace of mind, isn't it? Knowing your last line of defense just can't be messed with.
Absolutely. It forces a certain discipline in planning your retention. Because once it's locked, it is locked. But that discipline is exactly what gives you that robust defense.
Okay, so that handles the threat side. Now, let's talk about moving critical systems. Plan changes, migrating virtual machines, maybe from an old storage array to a shiny new one. That can feel like a real high-wire act sometimes. How do you ensure minimal downtime, or ideally near zero downtime?
Right, nobody wants downtime. HPE Zero Move is really designed precisely for this, for near zero downtime migrations. What's fascinating here, and really key, is that the source VMs, the original ones, they keep running during the replication, business as usual. But the real game changer, I think, is the ability to do non-disruptive testing before you commit to the final cutover.
Non-disruptive testing, what does that actually mean in practice?
It means you can essentially validate the entire migration in the new environment, test the apps, check performance, all without impacting the live production systems. You find any issues before the cutover happens. It avoids all that downtime, that uncertainty you get with the more traditional, failover-based methods.
Okay, so you can effectively kick the tires on your migrated systems before you actually cut the cord from the old one. That dramatically reduces the risk, I imagine, takes a lot of the stress out of it.
Exactly. Much less stressful.
All right, let's zoom out a bit. From local stuff to disaster recovery, maybe across different physical sites. What if you've got two separate data centers? Each has its own fiber channel SAN fabric, that high-speed storage network. And you need seamless replication between them, but, and this is key, you don't want to actually merge those SAN fabrics. You want to keep them separate.
Yeah, that's a common scenario. You want the DR, but you also want the isolation. Merging fabrics can be complex, risky even. The solution here is often FCIP. That stands for Fiber Channel over IP. Basically, it cleverly encapsulates those fiber channel frames inside standard IP packets. So you can link your independent SAN fabrics over long distances just using a regular IP network. Could be the internet, could be a private WAN. This means you'll get your replication, your disaster recovery between sites, but without all the complexity or the security worries of actually merging those fabrics together.
Okay, so it's like building a secure, almost invisible tunnel just for your high-speed storage data, but it runs over the existing internet or WAN highways you already have. That sounds pretty elegant.
It is. It leverages existing infrastructure while maintaining that crucial SAN isolation.
The art of high-performance data access and connectivity.
Okay, so protecting data is one massive piece of the puzzle, but making sure it's always fast, always accessible, especially when you've got complex distributed environments, that's a whole other challenge. Let's explore how these systems manage that high-performance access side of things. Let's take an HPE ElectroStorage MP array, maybe the B1000 model. It's set up with pure persistence across 2 data centers. Remember, that's the tech making 2 arrays look like one active system. Now say an application is running in data center A, but it's accessing a volume that for whatever reason has actively moved over to data center B. What's actually happening with that connection? What does the host, the server running the app, see?
Right, good question. In that specific case, the path from the host in data center A to the now remote array in data center B, that path will be marked by the system as active non-optimized.
Active non-optimized. Okay, what does that really mean? Is it bad?
Not necessarily bad, no. It means the I/O, the data requests, they still flow. Your application keeps working, which is crucial. But the non-optimized part signals that the traffic is taking a less direct path, probably over the intersite link, so potentially a bit slower. This status acts as a signal to the host's multipathing software. It's smart, it knows this path works, but it's not ideal. So it will intelligently prefer the local optimized path as soon as that becomes available again.
Ah, I see. So it's about maintaining access constantly, but always trying to get back to the fastest lane, like smart adaptive routing for your storage traffic. It keeps things going, but it's always looking for that optimal connection.
Precisely. It prioritizes keeping the application running while automatically optimizing for performance whenever possible.
Okay, sticking with pure persistence. What if you have hosts, servers in both buildings? Maybe it's a campus environment. And hosts in both buildings need, well, equal symmetric access to the volumes. Performance should be great no matter which building you're in.
Right. For that kind of symmetric access in a dual-site Alletra MP pure persistence setup, there's a specific setting. The host proximity parameter needs to be set to all.
Set to all. And what does that instruct the system to do?
It tells the system, essentially, treat both storage arrays as equally preferred for all connected hosts, regardless of which building they're physically in. This enables symmetric active paths from hosts in either building. So you get consistent, optimal performance no matter where the host sits within that campus setup.
Got it. So it's not just about can I access the data, it's about how well can I access it. And
Yeah.
all ensures everyone gets that equally good top-tier access. That makes sense for balancing workloads across a campus.
Exactly. Fair and fast access for everyone.
Now, let's switch gears slightly. A classic IT headache.
Mm.
Mixed client environments. You've got Windows users needing SMB access, Linux users needing NFS, and they all want to work on the same shared data. Historically, that's meant separate shares, maybe complex gateways. How does something like HPE GreenLake for file storage handle this?
Ah, yes. This is where GreenLake for file storage really simplifies things. It natively supports cross-protocol access. What that means is the exact same data set, the same files and folders can be shared simultaneously over SMB for Windows and NFS for Linux.
Simultaneously, without any tricks.
Right. No need for separate shares for each protocol, no need for some kind of clunky third-party gateway trying to translate between them. The system itself handles the coordination of metadata, file locking, permissions, all that stuff behind the scenes. So different protocols can safely and efficiently access the very same files at the same time.
Wow. That is a huge simplification. Just one data set, multiple access methods, takes away a whole layer of management complexity and potential points of failure or inconsistency.
Absolutely. It streamlines things considerably for admins.
Okay, let's really crank up the performance dial now. Think AML clusters, huge data sets, demanding workloads. If you're designing a new cluster like that, needing extremely low latency, super high throughput, what's the protocol you'd lean towards?
Yeah, for those really demanding AIML workloads where performance is just paramount, NFS over RDMA, specifically RoCE, that's RDMA over Converged Ethernet, is typically the recommended protocol with GreenLake for file storage.
RDMA, Remote Direct Memory Access. What does that actually do? Why is it better?
So RDMA allows data to move directly between the storage system's memory and the application server's memory. Critically, it does this without heavily involving the server's CPU in the data transfer process itself. This bypass dramatically reduces CPU overhead on the servers.
frees up the CPU for the actual AI number crunching.
Exactly. And at the same time, it delivers very, very low latency and extremely high throughput for the data movement. It's just ideally suited for the sheer scale and the speed required by modern analytics and machine learning pipelines.
Okay, now that's really interesting. It's not just faster storage, it's fundamentally changing how the data moves, bypassing the CPU bottleneck. That sounds absolutely critical for feeding those data-hungry AI models effectively. Shows how the hardware and protocols are evolving together to unlock these new applications.
Precisely. It's an end-to-end performance consideration.
Strategic insights, assessment, certification, and centralized control.
All right, so we've covered protecting data, making it fast. But there's also the crucial work around the storage, managing it, assessing what you have, ensuring reliability. Let's get into some of those strategic insights in our final section. When you're assessing a customer's existing storage setup, especially if it's, a mixed bag of different vendors, different technologies, how does something like the HPE Storage Assessment Framework, or SAF, differ from maybe more automated tools like cloud physics, for instance?
That's a good distinction to make. They serve different, though related purposes. Unlike a fully automated tool that tries to discover everything on the network, SF usually involves more, let's say, manual data collection. Think logs, specific performance metrics, configuration details, often gathered by a consultant working with the customer.
Okay, so more hands-on.
Yes, typically. And that gathered information is often emailed or securely transferred to HPE for analysis. It's generally a more consultant-driven, in-depth assessment. It works really well across those mixed vendor environments. And it can provide a different kind of insight, perhaps more qualitative, compared to purely automated discovery. It's about combining data with expert interpretation.
Right. So sometimes, even with all the automation we have, there's still a place for that human expertise, that structured, maybe more detailed manual look, especially when things are complex or involve multiple vendors.
Definitely. Context and interpretation matter.
Now let's talk critical applications. SAP HANA, for example, an in-memory database. Reliability and performance there aren't just nice-to-haves. They're absolutely essential. Business depends on it. What's a key benefit, maybe even a requirement, when choosing an HPE solution for that kind of workload?
A really key benefit, and often, yes, a requirement from customers or SAP themselves, is certification. HPE offers specific SAP HANA appliances and solutions that are fully SAP certified. Now, this certification isn't just some rubber stamp. It's a rigorous process. It guarantees that the whole stack, hardware, firmware, specific configurations meets SAP's demanding standards.
Standards for what specifically?
For high performance, for scalability as the database grows, and crucially, for built-in high availability. For something like SAP ATA, where the data lives in RAM, this certification is absolutely critical for integrity, reliability, and ensuring you get the performance SAP expects. It basically de-risks the entire deployment for these mission-critical systems.
Yeah, it sounds like it's all about trust and confidence, doesn't it? Knowing that the solution has been put through its paces and officially approved by the application vendor gives you that peace of mind, especially when so much is riding on it.
Absolutely. Peace of mind is a big part of it.
Okay, finally, let's loop back quickly to peer persistence, that active setup. What if a storage admin needs to resize a volume that's part of that peer persistence pair, but they try to do it from their local arrays management interface and they get an error? What's going on there? Why can't they just do it locally?
This highlights a really important principle for managing these kinds of distributed, highly available systems. In peer persistence, those volumes aren't just standalone things. They're part of a tightly coupled replication group mirrored across two arrays. Any change, like resizing, has to be perfectly coordinated across both arrays simultaneously to maintain consistency.
So trying to change just one side would break the mirror, basically.
Exactly. It would create an inconsistency, break the replication relationship. You can't do it via the local interface for just one array. The correct way is to use a centralized management plane. For HPE, that's often the Data Services Cloud Console, or DSCC. Using DSCC ensures that the resize operation, or any other change, is properly coordinated across both arrays and the peer persistence relationship. It maintains the integrity of that single logical mirrored volume.
Okay, that makes perfect sense. So the takeaway for you, the listener, is that for these complex replicated environments, a centralized control plane isn't just nice, it's essential. It prevents errors, ensures consistency. It really shows how greater resilience often requires more intelligent, unified management tools.
Well said. Complexity needs coordination.
We hope this deep dive leaves you with maybe a bit of newfound curiosity. What other sort of invisible layers of really sophisticated engineering are quietly humming along, ensuring the stability, the speed, the security of this digital world we rely on so heavily every single day? It really makes you think, doesn't it? About the incredible complexity, the constant innovation just hidden beneath the surface.